This video will continue reviewing in some small part the different levels of data, but primarily focus on some plotting, especially as relates to histograms and box plots, otherwise known as box and whisker plots. So this video is based on the Yoho National Park burn data. So this appeared in one of the problem sets. One of the variables was fire number. You can see these are not real numbers, they're effectively categories. And there's no inherent order or no inherent way to order these data. So fire number is a nominal level variable. Nominal data, the central tendency for nominal data is probably best summarized, and our options are pretty limited here. It's probably best done using the mode, so the category that appears the most in the data. And our best statistic, our best way to describe the dispersion, the amount of spread in the data around the central tendency, is the index of dispersion. That's not something we talked about much in the lecture, and we're not going to talk a lot about it here either. It's not something I will, honestly, it's not even something I'm going to test you on. It's just a keyword to remember if at any point in the future you need to quantify the dispersion of a nominal or ordinal level data set, then you can go back through your notes and find this thing called the index of dispersion and throw that into Excel and do it. Fire year, as the name indicates, year is part of this, and year is one of our kind of canonical, it's one of our classical variables for interval level data. So fire year is indeed interval level data. It is a true number, and because of that, our go-to statistic for central tendency, or go-to way of describing central tendency, is the mean, and our go-to way to describe dispersion is the standard deviation, or the variance. Now, those are kind of our defaults, but it is equally valid, and sometimes more than valid. Like I personally tend to default to the median and the median absolute deviation instead. The big reason to do that is the mean and the standard deviation are very strongly affected by outliers, data that do not follow the overall pattern of the data. So they're weird points. And again, the mean and the standard deviation are very strongly influenced by outliers. And in contrast, the median and the median absolute deviation are not. So we can do more things with a mean and a standard deviation. Like most of those hypothesis tests are based on means, for instance. We didn't learn how to do any of them with medians. So we can do more if we calculate a mean. But if we have outliers and we don't know what to do with them, then if we calculate a mean, we wouldn't want to do hypothesis tests with them anyway, because the outliers are messing things up for us. So as far as straight summaries go, if you have outliers, oftentimes a median and a median absolute deviation is a better way to go. Fire area, as the name implies, we're talking about an area in meters squared. This is kind of a geometrical measurement. There's a physical interpretation to areas. The zero matters. We can't arbitrarily add and subtract areas. And so fire area and all areas are ratio level variables. These are true numbers, just like fire years, and as such, the fire area, or our default statistic for central tendency, is again the mean, and for dispersion is again the standard deviation. And the same caveat applies. If we think that fire area has some outliers, kind of weird points in there, and we don't know what to do with them, then perhaps using the median and the median absolute deviation is a better bet. Fire area in hectares is the same as fire area in meters squared, still an area, still a ratio level variable. And biogeoclimatic zone code, these are clearly not numbers, they are categories, and there's no inherent way of ordering these categories. So like fire number, biogeoclimatic zone code is nominal, and our options are limited to pretty much the mode and the index of dispersion. So that's that. Let's go talk about plotting and some graphs. And even before moving into all of this stuff, let's go scroll down to some quickly drawn histograms. So if we were to take our data and kind of run it through a pivot table or something like that, and create a not a frequency diagram, a frequency table, we would get something like this. We have years and number of fires and area fired. I'm just using a subset of the data here. We could imagine for these kind of plots that the x-axis might be year, and the y-axis is the number of data points that falls within a certain bin. I keep saying we're going to jump to this, and I refer to things up here. So maybe we'll go look at the histogram that actually came out of the data first. So this particular histogram is based on the area of fires between 2000 and 2017. If you recall how histograms work, the x-axis is not a category. That's what differentiates it from a bar chart. A histogram always just uses one variable, in this case the area of fires variable. The height of the bars refer to the number of rows, and we get to add or consider a row to be in this bar if the value associated with that row fits within the category on the x-axis. So the first category, the first bin, as it's technically called, is between 10 and 5,010, so about 0 to 5,000. So if the value of this particular row is between about 0 and 5,000, which it is, then we get one kind of tick in here. So this data point would be one of the 9 data points for this bar. This data point does not fall within 10 to 5010, and so it is not included in one of these. That 130,000 goes into this bin, actually. And so pretty much data point by data point, we count and we see which bin it falls into, and in the end we count up how many data points are in each bin, and that creates our histogram for us. So now let's go look at our theoretical curves here. So remember the x-axis would be, in effect, our bin, or our bin widths, and the height here, the number of rows, the number of data points that fall in each bin. We learned some terminology that applies to the distribution of data. And so distribution, or the term distribution, really just means the shape of the data when plotted like a histogram. So one of the terms that we learn, one of the descriptors for a distribution, is how many peaks it has, how many bumps does it have. This particular plot has one bump. This plot has 2 bumps. This plot down here has 3 bumps. Bumps we call modes. So remember that the y-axis is the number of data in a certain category, and the mode tells us which category had the most counts in it. So whatever bin, remember bin is on the x-axis, whichever bin has the highest number of counts is the mode of the data set. So here we have one mode, so we call it unimodal, one modal, one mode. This would be a bimodal, 2 modes. And down here we would have either a trimodal, but really we just say multimodal after that. So we have uni for 1, bi for 2, and multi for anything greater than 2. The next thing we look at is the symmetry of the plot. And when we talk about symmetry, we're not really looking for exact things. Theoretical curves will either be exactly symmetrical or exactly not symmetrical, in the case of like the chi-square distribution, which can never be symmetrical. Real data are not that nice, so we're looking for approximately symmetrical. If it is approximately symmetrical, then we say it is symmetrical. That's not very exciting. A plot like this, which is bimodal, is also symmetrical. The kind of opposite of symmetrical has a somewhat fancy term called the skew. And so it is represented by something kind of like this, where we took the mode, the peak of the data, if you will, and we pushed it off to one side. So we kind of stretched this section out and again took the mode and pushed it off to one side. So when our mode is no longer in the middle of our data set, when it is no longer symmetrical, then it is skewed. And whatever direction we pulled from, so whichever one has this kind of long tail, that's what we call this, that is the direction we assign the skew. So this is a positive skew or a right skew because it has the long tail. Not to be confused with the mode being here on the left. So this is not a left skew because we have the bump. It is a right skew because it has the long tail. Conversely, we have this one. Now we've taken the bump that would have been here and we've shifted over to the right, which means we have a left skew because it has the tail, or a negative skew. It is still unimodal because we still only have one bump. So this would be a unimodal left skewed distribution, unimodal right skewed, and a unimodal or unimodal symmetric distribution. Bimodal and symmetric. This is bimodal because we have two humps, and a left skew because that's where the tail is pointing. And this one is multimodal and a right skew. So notice in all of these we have the skew and nothing interesting happens in the skew part. It is still skewed to the left, and it's still okay to have modes way out here and have funky things happening. This is still multimodal, and it's still a right skew because most of the data is over here, and this is still the right tail. So a right tail, right skew, positive skew, whatever you want to say. So those are just kind of some theoretical curves to think about. So that brings us to something like this, or going back to this. So this is the actual plot of the area of fires data. And so we can see, I'll go get a red pen going. Our other distributions generally started at 0 and went up. They don't have to. So here we're just starting at the left, rapidly decrease. It goes all the way down to 0. Nothing happens here. And then we get a bump at the end. So it's somewhat kind of like this, except it doesn't have that mode over there. So how would we describe this data? Well, it's still right skewed because most of the data is over here and then it decreased and went down. So there's our right skew or our positive skew. But we have a very significant jump at the end, enough that I would call this bimodal. So one mode is here. And even though this is the true mode, the single highest number of counts are over here, I would call this one high enough to count as a second mode. This definitely breaks the pattern, and as data analysts, we should consider what is going on over here. In fact, anytime we make a histogram, we should go out of our way to change the binning scheme and make sure that we're not creating any artifacts or hiding things by having our data arranged in units of about, or widths of about 5,000. So I wanted to call these bimodal. We can demonstrate that, for instance, by changing this to a bin width of 1,000. And we see, once I clear this out so we can actually see, now our first bin, there were 4 counts, and our second bin is also 4 counts. So now it truly is bimodal. There's 2 different numbers that have the exact same counts. So if nothing else, hopefully that is proof of 2 things, that yes, the data were bimodal, and as well the importance of playing with your bin width to make sure you fully understand what's going on with your data. So that's histograms. One last thing I wanted to do is box plots, but we'll actually do that in the next video.